In this video, I want to talk about the general solution for step and natural responses of RL and RC circuits. So far we have seen the step and natural responses of RC circuits. So both of those responses had the same differential form. So it would be nice if we can have a general solution for both of them. So to achieve that general solution, let's just represent the unknown quantity by xt or x of t. So this can represent four possible values, either voltage of an inductor, current of an inductor, or voltage or current of a capacitor. So the general differential equation, or the general first order differential equation with k representing as a constant, looks like this. We have dx over dt plus x over tau equals k. And you know that tau is the time constant. So if you remember, for an RL circuit, the time constant is L over R. And for an RC circuit, the time constant is RC, or the multiplication of R and C. So since the sources that we connect to such circuits are constant, we know that after all the transient changes happen, the final value for either of these four variables is going to be constant. So whether it is the voltage of the inductor or its currents, or the voltage or current of a capacitor. So we can say at t equals infinity, xt is a constant value. We call it xf, or the final value. So in this case, the derivative of dx over t is going to be 0, which basically means that xf over tau equals k, or in another form, xf would be equal to k multiplied by tau. So this is one of the observations that we have. So now we know the procedure for solving such a differential equation. We need to separate the variables. On one side we need to only have x, and on the other side we only need to have t. So to do that, first what we do is that we move x over tau to the right side, calculate this summation. It's going to be negative x minus k tau over tau, and we have seen before that this is actually xf, or the final value of f of x. So that means that dx over dt equals negative x minus xf over tau. Now we multiply both sides by the differential time, and then we divide both sides by x minus xf. So if we do that, on the left side what we are left with is dx over x minus xf equals negative 1 over tau dt. Now what we need to do is we need to take the integral over the required period. So the period for x is going to be for x at time t0 until x at any given time t, and for the t is going to be between t0 and t. So you have seen how this integral can be calculated. So the right side, this part, we only have the integral of the differential time. Again, we have changed the variable for representation purposes to avoid the confusion. So this will be t minus t0. For the left side, we know the integral here is actually natural log of u minus xf, and u can change between xt0 to xt. So if I just replace these two limits, what I get is natural log of xt minus xf over xt0 minus xf. So we have ln xt minus xf over xt0 minus xf to be equal to minus 1 over tau multiplied by t minus t0. So since we want to find the equation for xt, what we need to do is that we need to take both of the sides of the equation as an exponent of the Euler number, or E. So if we do that, the left side is going to be only xt minus xf over xt0 minus xf, and the right side is going to be e to the negative t minus t0 over tau. And then by just simple algebraic manipulation, this is the final equation that we get. The variable x at any given time t equals the final value of x plus the initial value of x minus the final value multiplied by e to the negative t minus t0 over tau. So let us take a moment to actually go over the equation. So this is the equation that we get. The variable at any given time, remember this variable can be the current or the voltage of the inductor or the current or the voltage of the capacitor, equals its final value plus the subtraction of the initial value minus the final value multiplied by this exponential function. So the unknown variable as a function of time equals the final value of the variable plus the initial value of the variable minus the final value of the variable multiplied by e to the power negative t minus the time of switching divided by the time constant. So this makes things much easier as opposed to solving the differential equations several times for each one of the variables that we want to find. So let us go over the procedure now. So given this outcome, we can summarize the procedure for finding the natural and step responses of the RC and RL circuits as follows. First, we need to identify the variable of interest for the circuit. So for RC circuit, it is most convenient to choose the capacitive voltage or the voltage of the capacitor. For RL circuit, it is best to choose the inductive current or the current of the inductor. So even though I said these two are more convenient, but it doesn't say that you cannot choose the current of the capacitor or the voltage of the inductor. But between the four variables that we can have, these two are more convenient. The second step is to determine the initial value of the variable, which means that what is the value at time t0, basically the time that we change the position of the switch. So you need to keep in mind that if you choose the voltage of the capacitor or the current of the inductor as your variable, it is not necessary to distinguish between t at t1 epsilon before t0, or I can just show it as t0 minus and 1 epsilon after t0, or I show it as t0 plus. Because if you remember from the equations that we had for the capacitor and the inductor, for the capacitor, its voltage was L di over dt. For the capacitor, I was C dV over dt. So if you remember from before, we said that for the inductor, the current cannot change suddenly because that requires infinite amount of voltage, which is not possible. The same is true for the voltage of the capacitor, which cannot change suddenly because that requires infinite amount of current. So this means that the current of the inductor needs to be continuous at all times. Also, the voltage of the capacitor needs to be continuous. And that's why it is preferred to choose the current of the inductor and the voltage of the capacitor if we want to solve an RC circuit, because we can assume that right before you change the switch and right after you change this switch, these variables do not change, so they remain at their value. You cannot say the same thing for the voltage of the inductor or the current of the capacitor. So for the inductor, the current cannot change suddenly, but the voltage can. For the capacitor, the voltage cannot change suddenly, but the current can. So that's why if you choose another variable, you need to remember that its initial value is defined at time t0 plus. So the value at time t0 minus is not the same as the time as t0 plus if you choose the voltage of the inductor or the current of the capacitor as your variable xt. Then the next step is to calculate the final value of the variable, which is its value at t going to infinity. And for doing that, since we are working only with constant sources, that means that if we want to find the current of the capacitor, we need to know that at time equals infinity, the current of the inductor, we need to know at time equals infinity and inductor acts as a short circuit. For capacitor, we know that the capacitor at time equals infinity acts as an open circuit. So that's how we can create alternative circuits for t equals infinity and find their final values. And then the last step is to calculate the time constant for the circuit. So it means that we need to know the equivalent inductance in the circuit, we need to know the equivalent resistance, and for the RL circuit, the time constant is L over R. For the RC circuit, the time constant is R multiplied by C. And by doing that, we can plug all these values that we have found through these steps into this general equation, and we can find the general solution of an RC or RL circuit. So in this video, we learned how we can calculate the general response of RL and RC circuits, and we went through a procedure that can help us find the solution much more easier than solving the differential equation.